The atmosphere is defined as being the gaseous envelope surrounding a celestial body. In more simple words, the atmosphere is the collection of gases that is held around the Earth by gravity. There are various major gases that make up our atmosphere. The most common gas is nitrogen, which accounts for about 78% of the atmosphere. Oxygen is sometimes misconceived as being the most abundant gas, but it represents only 21%. Just under 1% is argon, with carbon dioxide and a few others making up the rest. There are many more gases that are found in such small quantities that we regard them as trace gases. Some of these include neon, helium, methane, ozone, and hydrogen. Water vapor is another gas in the atmosphere. It's found in very small quantities, but without it, there would be no weather. So much of our understanding of weather is to do with the behavior of water in our atmosphere. It can become visual to us in many ways, such as clouds, rain, snow, hail, frost, and so on. The relative amounts of the gases stays fairly constant up to about 60 kilometers above the Earth. Thereafter, gravitational separation alters the composition of the atmosphere. However, there are other changes, primarily in temperature, that allow us to structure the atmosphere into segments. The first of these segments, or layers, is called the troposphere. This layer is closest to the Earth, and its defining characteristic is the marked decrease in temperature with height throughout the layer. Where the temperature no longer decreases with height defines the upper part of the troposphere. This upper boundary we call the tropopause. Here, temperature is constant with altitude. The thickness of the troposphere, and therefore the height of the tropopause, is not constant across the Earth. Over the poles, the height of the tropopause is about 8 kilometers, whereas over the equator, it's about 16 kilometers. The average height is 11 kilometers, which is found at about 45 degrees latitude. What controls the height of the tropopause is the general temperature of the troposphere. As a general rule, the colder the troposphere, the lower the tropopause, and vice versa. The extremes of this are demonstrated very well over the poles and the equator. It follows that when the troposphere is at its coolest, i.e. over the poles in winter, then the tropopause would be at its lowest. However, there are places where the tropopause folds or breaks. This is where we find a significant difference in the temperature in the troposphere, and therefore a significant tropopause altitude change. The first of these is at about 40 degrees latitude. The warm air circulating from the equator meets much cooler air circulating from mid-latitudes. This temperature difference in the troposphere causes a height change of the tropopause. The second tropopause break is at higher latitudes of about 55 degrees, where polar air meets tropical air. This happens along the polar front, which we'll talk about much later on. Again, there's enough of a temperature difference within the troposphere to cause a tropopause height change. The last of the tropopause breaks occurs at even higher latitudes, and is evident mainly in the northern hemisphere and in winter. This is where very cold Arctic air meets less cold polar air. It occurs typically at about 60 to 70 degrees latitude. The temperature difference here is also enough to cause another tropopause fold or break. If we know that temperature decreases with height, then it follows that the closer the tropopause is to the Earth, the warmer it will be. Over the poles, the tropopause temperature is about minus 50 degrees Celsius, and over the equator, it's minus 80 degrees Celsius. As we can see, at the tropopause, temperature increases with latitude. Of course, this is the opposite from what happens at the surface, where temperature decreases with latitude. Why is the tropopause so important to us? Well, the tropopause signifies the start of a marked temperature inversion. This effectively limits the vertical movement of air and clouds within our atmosphere. It's useful to know, then, that the tropopause usually signifies the limit of cloud development. However, the tropopause does tell us other things. As a result of very low densities in the upper atmosphere, the upper winds tend to be very strong, and in some cases form narrow bands. These are called jet streams. These in themselves can be beneficial if our flight goes in the same direction. But with these jet streams there is a likelihood of significant turbulence. We call this clear air turbulence, or CAT. Having discussed the troposphere and its upper boundary, the tropopause, we'll now look at the next layer in the atmosphere, called the stratosphere. The stratosphere extends from the tropopause up to about 50 kilometers above the Earth's surface. The temperature structure of the stratosphere is dominated by the presence of ozone. Ozone is formed when solar radiation splits oxygen into its two individual atoms. These are then free to combine with others to form the gas ozone. This process releases energy into the surrounding air, and therefore heats up the part of the atmosphere where ozone can be found. Concentrations of ozone are at a maximum at around 20 to 25 kilometers above the Earth's surface. Due to latitude effects and the depletion of ozone during the polar winter, the temperature through this part of the stratosphere can vary from minus 30 to plus 20 degrees Celsius annually. Superimposed on the Earth is a colour representation of ozone depletion. The purple area over Antarctica is showing where we have the greatest amount of depletion. This is due to a number of reasons, and the discussion of this is outside the scope of this lesson. Where the temperature starts to fall again signifies the top of the stratosphere and marks its upper boundary. This boundary is called the stratopause. Above the stratopause is a much cooler layer where the temperature continually decreases with height. This layer is called the mesosphere. It usually extends about 80 or 90 kilometers above the Earth's surface. At the top of this layer, we have some of the coolest temperatures encountered, sometimes as low as minus 180 degrees Celsius. The upper boundary to the mesosphere is called the mesopause. Above the mesopause is a layer called the thermosphere. This zone is characterized by a rapid rise in temperature up to about 200 kilometers. Temperatures here can be between 600 and 2000 degrees Celsius. The lower part contains a zone called the ionosphere, where we can have such high ionization levels that long-wave radio waves can be reflected back to Earth. Where this reflection is at a maximum is at roughly 110, 160 and 250 kilometer levels. These are respectively called the Kennelly, Heaviside and Appleton layers. The upper part of the thermosphere is known as the exosphere. This layer starts at about 700 kilometers above the Earth's surface and is highly tenuous and undefined. All the layers we have analyzed have been defined by their unique temperature profiles. However, most of our flying and our weather is contained within the first two layers of the atmosphere, namely the troposphere and the stratosphere. Within these two layers we have many properties which are important to us, like density, pressure, and temperature. However, our atmosphere is so very variable from day to day, it's been necessary to construct a model atmosphere for help in calibration of instruments and aircraft testing. This model atmosphere is known as the ICAO International Standard Atmosphere, or ISA, sometimes referred to as ISA. However, the model only extends to 32 kilometers, which is about 105,000 feet above mean sea level. ISA assumes that, at mean sea level, the temperature is 15 degrees Celsius, pressure is 1013.2 hectopascals, and the density is 1,225 grams per cubic meter. From the surface, up to 36,090 feet, or 11 kilometers, the temperature decreases at a constant rate of 1.98 degrees Celsius per 1,000 feet, or by 0.65 degrees Celsius per 100 meters. The temperature decreases down to minus 56.5 degrees Celsius. This is where we find the tropopause in ISA, and the temperature no longer decreases with altitude. From this point onwards, we have the stratosphere, and ISA assumes the temperature within the first part of this layer remains constant at minus 56.5 degrees Celsius up to 20 kilometers, or 65,617 feet. From 20 kilometers and upwards to 32 kilometers, we have a gradual increase in temperature by 0.3 degrees Celsius per 1,000 feet, or 0.1 degrees Celsius per 100 meters. If you remember, this is the part of the stratosphere that contains the gas ozone, which causes the surrounding air to warm. All aircraft instruments are calibrated to ISA. Therefore, it's essential to know just how much the actual atmosphere on a given day differs from ISA. The simplest method we use to analyze this difference is through comparing the real temperature to the standard ISA temperature. This is known as the ISA deviation. In other words, how much the real atmosphere deviates from the standard atmosphere. Let's recap the ISA lapse rate within the troposphere. Remember, we said ISA assumes that the sea level temperature is 15 degrees Celsius. The temperature then fell by 1.98 degrees Celsius per 1,000 feet. In the diagram, we can see that at an airfield 1,000 feet above sea level, the ISA temperature should be 13.02 degrees Celsius, but the actual temperature is 20 degrees Celsius, which is much hotter than the standard. We need to calculate how much hotter than ISA the real atmosphere is. A simple mathematical calculation shows that the atmosphere is 6.98 degrees Celsius hotter than ISA. The representation of this information is important. The best way to understand it is by reading the ISA deviation backwards. We can say that the real atmosphere is 6.98 degrees Celsius hotter than ISA.